title, but it's something about strong ballistic transport and Lieb-Robinson bounds for quasi-periodic operators. So the goal of this is to present some concept about discrete Schrödinger operators, which was studied in several papers. So it will be called strong ballistic transport. And I think there is still some mystery about it. So it's known for several concrete classes of operators, but there is no general theory of it, even though it seems quite natural from physical and from operator-theoretical point of view. But I will start from a little bit far away, because the motivation for that actually comes from some many-body quantum systems. Also, the advantage of this is that when the second part of the talk will be self-contained for those people who show up at 2. Okay, so we're going to be talking about very special class of many-body quantum system, which is called isotropic XY spin chains. So to define quantum system, we need Hilbert space, Hamiltonian, and time evolution for observables. So Hilbert space is just tensor product of a finite number of samples of C2. So it's n minus n plus 1 identical particles. Each one has only spin. The Hamiltonian is basically the hopping type interaction. The Hamiltonian has hopping term and external magnetic field term. So particles can hop from a site to its neighbor. So this is the kinetic energy part. And the sigma are just the standard Pauli matrices. So J here means it acts on the jth particle. Okay, and the system is put into external magnetic field, which is coupled with the Z component of the spin. So this model is called isotropic XY spin chain, isotropic because the coefficients here are trivial. And basically there are several different properties you can consider about this spin chain, and most people are interested in properties that are independent on the size of this lambda. So there are some difficulties in defining this for infinite lambda, because the Hilbert space will be non-separable, and there are difficulties with the operator theory in that case. But okay, and we are going to be looking into transport properties. So let me describe what kind of transport properties we're going to be looking at. So basically, we look at the evolution of observables and see how the correlation between two observables change with time. So to explain more rigorously, let me define what is a local observable. So local observable, so set of local observables, with respect to some set S2 sub S, okay, let's say S subset of lambda. So it's observables which act non-trivially only on the particles from S. And on the other particles, they act as identity. For example, sigma xj is a local observable with respect to the site j, because it acts as identity on the other particles. Okay, so let's have two observables, A and B. S1, B belongs to O of S2, and such that the supports do not intersect. Then obviously these two observables commute. But this commutation will immediately break down if we start the time evolution of one of the observables. So question, can we still say something about the commutator, let's say for small times? So let's look at the commutator A of t b. So can we make some bounds of this commutator if the time is not very large? And turns out there is a very general result called Lieb-Robinson bounds saying that yes, there is a bound like this. So Lieb-Robinson. So it was originally discovered by Lieb and Robinson and rediscovered by Nakhtar, Gale, and Sims. So it claims that this norm depends. This norm is bounded by the following quantities. So some constant C, norm of A, norm of B, e to the minus all places is equals to C1, C2, distance S1, S2, minus some parameter V LR times T. So LR stands just for Lieb-Robinson. So the statement is that there exists a number VLR such that this bound holds for all t. So there exists VLR dependent only on supremum over J, absolute value of the magnetic potential. So this number does not depend on the size of the system. So if we are originally given an infinite sequence, so no matter how large window we cut from the system, the constant in this bound will be the same. So in a sense, it's a statement about infinite spin chain, even though we haven't defined infinite spin chains. Okay, so
this actually probably holds for much more general ones than you have.
yes, so it holds for very general quantum spin systems, not even just one-dimensional. So I think there are higher dimensional results as well. Yes, so let's look at this bound a little bit. So first, if t equals 0, then it doesn't really tell us anything new. Because the commutator is 0, here we see that it's bounded by the exponent of the distance, which is weaker. So if t is very large, then this bound is also useless, because we can always forget about this term, just bound the commutator by the norm of the operator. It's a unitary transformation. Okay, so the situation where this bound is useful is where t is sufficiently small. Then it says that basically correlations decay exponentially, so the exponential decay remains if the time is not very large. And so what exactly does not very large means is controlled by this parameter v.
So t doesn't have to be small, it just has to be small compared to the distance.
Yes. Yeah, that's correct. Smaller compared to the distance, but what exactly means smaller compared to the distance is contained here. Okay, so and then the question is, what are the possible values of v for a given system? Obviously, if it holds with some v, then it holds with any larger v, because the exponent will just increase if we increase v. There are two negatives here. So the set of possible values of v is some interval, some unbounded interval. So the actual question is that what's the smallest possible value of v for a given system such that this bound holds? And there are three interesting possibilities. So let me write them down here. So first is that actually it holds with v equals 0. So VLR belongs to 0 plus infinity. So this is something that's called zero velocity Lieb-Robinson bound, and it's actually an evidence of many-body localization, because it basically tells that there is no transport in the system. I mean, up to some.
Yeah, if v is 0, right?
Yes, if we, yeah, I mean, so if this is the set of possible values of v, then this estimate holds with v equals 0, then there is no transport, sort of. So, and there are examples, I mean, for, yeah, huh? You want to say something?
Well, I guess you could have slow transport, right? I mean, you could have like diffusive transport, which would be a square root or something like that.
Yes, but still, I mean, there is a bound like this, which is uniform in time as t goes to infinity. So diffusive transport is actually, I'm not sure it falls within this regime, because it just tells us that the correlations are uniformly bounded in time. So no matter how much time you take. Yes, so diffusive is actually the next regime. Okay, so I will tell you examples for each of the three possibilities, but I want to talk about integrability first, because they will put them in a more natural context. So second case is that VLR can be arbitrarily small, but cannot be made 0. So this is something which is called anomalous Lieb-Robinson transport. So there is some special example where this is a Fibonacci Hamiltonian type sequence for which this estimate holds. And this is a result by Domanik, Lukic, Jessen, and Lem. And basically the correct version in this case would be that there is some fractional power of t, as you mentioned, which depends on some dimension of the spectrum of the correspondential integer operator, which I'll probably mention in the end. Okay, and the third option is the one we're actually interested in, is the case where v is bounded from below. So VLR belongs to some v0 plus infinity. So in this case, I will not distinguish between open and closed bounds. It's probably another difficult question, but I don't know it to this extent. So this is basically a class of 13 interesting cases where you can show that this velocity cannot be arbitrarily small. Okay, and then the question how to find out which of these cases holds for a given system. Again, I think that for general quantum spin system, it's a very difficult question. Even this, because if you know this, you know a lot about many-body localization, which is not really known. Yeah. So, but about this particular class of systems, there is much more known because they're integrable. So let me explain in which sense they're integrable. Basically, you can construct a certain Schrödinger operator which will contain in itself all the transport properties of the system. So integrability is delivered by so-called Jordan-Wigner transform. So I will just describe it very briefly. So basically the idea is to construct a certain collection of observables such that the evolution of these observables is given by some usual Schrödinger equation for one particle. This will be the sense in which they're integrable. So these observables constructed in the following way. So let's say Ck equals sigma z m, sigma z m plus 1. So remember, m is the starting point of the interval. So we take product of this sigma z until we reach k minus 1, and then multiply it by the annihilation operator. So 1/2 sigma x k minus I sigma yk. So you have a collection of these observables for k equals m, m plus 1, and so on until we reach m. So it's some computation which I will not really do here, but basically if you construct a vector of these observables, so let's say Cm of t, Cn of t, then you can show that this evolution, which is kind of it's a linear operator on observables, but it acts from two sides. So in this basis, it's actually just a usual, it's an operator that acts just from one side, and which is just the Schrödinger type evolution. So e to the negative 2i t h effective times this same thing of 0. Okay, so this
that effective one is diagonal, or
I will write it down in a second. Just so basically, if we take these observables and their conjugates, you can build any other observable from these ones. So integrability in the sense that there are some special observables whose evolution who form a complete set in a sense, and whose evolution is given by the usual Schrödinger equation. So now the focus of attention is this operator. Okay, let's see. I need that, I need this, but okay, let me move there. So H effective will be actually the following. It will be discrete Schrödinger operator with this potential, as simple as that. So nu m so there are ones here, and this is 0. So it's a finite dimensional discrete Schrödinger operator with Dirichlet boundary conditions. But then, okay, so technically it depends on lambda, but now, since we are looking at the properties that are uniform on the sides of lambda, once we switch to Schrödinger operator, we can look at the whole line. And then when we need to look at the interval, we just cut the submatrix from the matrix. So basically the statement, which is kind of not completely rigorous, but that all transport information about all these systems with different lambdas are contained in this operator if we extend it to the z line. Okay, and fortunately there are a lot of different results about transport properties for Schrödinger operators, but then there is a problem that when we try to write down some transport estimate for this one and use Jordan-Wigner transform, so because the transform is not local, so the transport bounds get weaker, and some of the certain bounds that exist are not enough. So this is why we need actually something that's called strong transport. So let me give a quick overview. Yeah.
The Hilbert spaces that tensor product.
Yes.
But e to the minus 2i is not acting in that Hilbert space, right?
Well, it acts on this vector of observables, just as a multiplication by matrix.
So it's just an n by, it's an n.
So this is just n minus m plus 1 by n minus m plus 1 matrix. So, but this is a matrix of operators. So
Acts on operators, but not on, well, it's act on operators which act in that space.
yes, that's correct. But then everything is contained in this matrix, and the matrix itself is much more simple. So this space has dimension like 2 to the power n minus m plus 1, and this is actually a matrix which is n by n. So the problem kind of simplifies.
gem daggers are creation operators. They're creation operators in Fock space, so you can kind of understand them as them giving you the 1 0 0 0.
Yes, that's correct. Yeah. Okay, so basically we're interested in some transport properties of these infinite Schrödinger operators which behave well with respect to that transport. So after doing the transport, we can get some information for this. So let me first, okay, so I promised to give some clarification for these examples. Yes, so if you put something random in, you actually, so there is a paper by Hamza, Simpson, Stolz. So they consider exactly the situation you're discussing. So when these new are random variables, then the spectrum of the Schrödinger operator in infinite line is purely point, and that corresponds to absence of transport, at least. So they prove Lieb-Robinson bounds in the ground state. So mu J, let's say. So I'm not completely sure. So I think they can only apply these operators to the ground state of this spin system, but I'm not sure about the exact formulation. It's just basically they show that in certain situations this V can be chosen to be 0, but it's not as general as for any observables, because then it would mean many-body localization. So I think their statement can be understood as many-body localization in the ground state. But I'm not an expert in this. Okay. Huh? Well, no, okay. So once we have this bound with 0 velocity, this can be called many-body localization to some extent, because this is a many-body system. Well, this is a many-body system, isn't it?
But it's quadratic in the.
No, this Hamiltonian is many-body, right? Well, yes, it's not a real many-body system, let's say it like that, but it's an example in which something can be said.
Right, okay.
Okay, that's correct, yeah.
And when you mentioned this result, this is about putting a random J isotropically between sigma x and sigma y?
Well, it says basically it's about putting random new independent identical distributed random variables here.
Many-body localization when you have real interaction, but it may be true that we don't even understand it properly in this case.
Yes, I think even in this case there is no complete understanding, but there are some results which show that sometimes this V can be 0. Yeah. It's just an example. So basically, very roughly, in some cases, point spectrum for this operator corresponds to 0 velocity here. Now, the second.
One thing I find confusing is what you have this 1, 2, 3 here.
Yeah.
That 1, I think you really mean that 1 should be 0, right? I mean, that's what you mean when you mean localization or some diffusive behavior. I wouldn't say it's 0 to infinity. You don't want anything to be bigger than 0.
Well, I mean.
So that's just a
well, it's just a convenient way of saying this, because it's difficult to write down what it means that V can be arbitrarily small but non-zero. If I say, let's say, VLR greater than 0, it still doesn't tell me can it be arbitrarily close to 0. It's just a question of notation.
But number 1 and number 2 would seem to overlap, and you don't really want to.
So number 1 is saying that the bound is true for all V.
Yes. I mean, this is if and don't leave statement. So the bound is true if and don't leave V belongs to here. So in number 1, it's true for any velocity. In number 3, it's true only until this V0.
Okay.
So it's necessary sufficient condition, basically. So it's the set of all velocities for which the bound is true. That's why they're different. Okay, so here there is an example by, as I mentioned, Domanik, Lukic, Jessen, and Lem. So where nu is the sequence which comes from the Fibonacci Hamiltonian. So the corresponding Schrödinger operator has singular continuous spectrum. and there are lots of fractional type transport bounds. And turns out that in this case, you also get a fractional type bound on the Lieb-Robinson velocity. So Fibonacci type. Okay, and here there is a result by Domanik, Lukic, and Jessen. For periodic sequences, so periodic, and the one I'm going to talk about for quasi-periodic. Quasi-periodic with AC spectrum. So basically, rough intuition would be that localization corresponds to zero velocity, singular continuous spectrum corresponds to some fractional velocity, and AC spectrum, at least in some cases, corresponds to like ballistic type behavior.
Yeah, I guess I asked you this question, but do you need everything to be quasi-periodic, or if you have some mixture of periodic, and suppose I have something quasi-periodic, and I have some mixture of quasi-periodic, and I have some mixture of point spectrum and AC spectrum, which of course is quite possible.
I'm not sure. So I think at least the argument I have only works in the case we have purely AC spectrum, and it's actually quite indirect. So I will explain why. So there is no like direct corollary that AC spectrum implies transport. Corollary is like that for certain class of systems, the conditions for AC spectrum are the same as conditions for transport. So it's not a direct statement. And the question whether there is a direct statement is open, and I think very interesting. Okay, so there is some kind of evidence here, and let me try to explain what kind of conditions we need for the transport of this operator to have some hopes of proving something for many body systems. So we need kind of very strong transport type conditions. So let me, okay, now we can actually forget about spin systems. So this is kind of the second part of the talk about Schrödinger operators now. Don't forget it like completely, but so we are now in the Schrödinger operator on Z. So H psi n equals psi n plus 1, psi n plus 1 plus nu n psi in L2 of Z. So there are some results. So first, what is the transport we are talking about? Let me give some more precise definition. So we'll look at the following thing. We'll look at the position operator. So let's x psi n equals n psi n. So x is the operator that measures the coordinate. So now, transport basically means that the coordinate of the particle grows in time. So particle moves somewhere. So we'll look at the evolution of x of t. So f x of t is e to the I ht x e to the minus I ht. So we're looking at x of t. Let's say, okay, so let me write t capital. So we look at the operator x at the moment t and measure it in some state. So we consider the following object. And let's also take absolute value because we are interested in the absolute value of the coordinate. Otherwise, the particle can spread to the left and to the right. The whole thing can cancel. We don't want that. We want, this is still transport. So we want to capture that as well. So transport, one way or another, is the rate of growth of this function.
So you assume that psi is a nice localized L2 thing. So
Yes, so I assume that the psi initially is in the domain definition of this operator. Then you can actually prove that it will stay in the domain forever, because difference between x of t and x is a bounded operator. Okay, so let's actually have. So, and turns out there are actually some good results about the growth of these operators, but they are not precise enough. So typical results that are known is some estimates which date back to Giarneri Combs, I think. So they look at the following. They look at the Chizawa average of this. So I'm not sure what exactly Jordan-Wigner proved, but there is a nice review paper by Yoram Last, which is called Quantum Dynamics and Singular Spectra, I think, in which he describes all that's known about this. And actually, there is a so if you look at this quantity, there is a complete description. So if the so if this quantity is, so if the spectrum of the operator is purely point, then this just remains bounded. So bounded. In the case the spectrum is purely point, so behaves like t to the power alpha for 0 less than alpha less than 1 for singular continuous spectrum, and is bound. It behaves like t, so bounded from below by some constant times t for AC spectrum. So this alpha is actually some kind of the Hausdorff dimension, either of the spectrum or of the spectral measure. I can't remember exactly. Probably of spectral measure. And basically the results, so this result actually
That's a general fact, I suppose.
yes, it's a general fact. It's not a very difficult fact. It dates back to Fourier transforms of measures, basically. And this result actually has the properties that you mentioned, that if the operator has coexistence, then the bound depends on to which subspace psi belongs. So if the operator has point part and AC part, then if psi belongs to point part, it will stay localized. If psi belongs to AC part, it will propagate. So this is a complete result, but unfortunately this bound does not translate into Lieb-Robinson bound because of the non-locality of that transform. So what can be better than that? There are two things that can be better than that. So we are now in this regime. So I'm only interested in this regime right now. So better. So there are two possibilities for it to be better. First, just remove this Cesaro average. Just say that x of t psi psi. So it value greater or equal in c. So it value of t. Okay, then that's value of t, I guess. Okay, so this turns out that this is strong, but it's still not enough to say something about Lieb-Robinson bounds. Although bounds like this became popular recently in the papers by Zhang and Zhao. So there are 2 or 3 papers by them. They prove this for a large class of quasi-periodic operators, including those that I cannot cover. But they only can get bounds like this or slightly weaker than that. And this is an interesting thing, but it's not. It seems that it's not enough to say something about spin sheets. So we're interested in something even stronger than that. So what can be stronger? So a stronger statement would be that if you look at the coordinate operator x of t and divide it by t, so then it would be nice if this operator converges to something. Q. So let's call the limit operator Q in the strong sense. And yes. So if yes, and the kernel of Q is trivial. So this is what I call strong ballistic transport in this talk. So this is so I think this seems like a very natural definition, because basically it tells us that the wave packet, if you normalize it, it becomes localized in infinity. Because if you take any state psi, then if you rescale it correctly, you can tell exactly where it's going to be located on infinity.
Yeah, but I guess I might ask whether you want the spectrum of this guy to be positive or something like that. If I have absolute values with it.
Well, so this is basically this condition. So if the kernel is trivial, there is a positive subspace and negative subspace. So positive subspace will be particles that localize.
Well, you wouldn't have a strict. You don't have a strict speed then, right?
Well, the speed depends on the initial data. Okay. So there is an operator of speed. Okay. So speed is also an observable, which is this operator Q. So this can be considered some kind of asymptotic velocity. So this concept was introduced first by Ash and Knauf. So they considered continuous periodic operators and proved that this limit actually exists. And this approach was used also by Domanik, Lukic, and Jessen in this paper, which extended to discrete case. So periodic. Okay. So basically, the goal of this talk is to explain that this concept, at least to me, seems very interesting and still not very clear.
So they do this for periodic Schrodinger operators?
Yes. Actually, they can also do periodic Jacobi matrices. So the leading coefficients in XY spin chain, they can also be periodic. So their result is more general. For quasi-periodic, we cannot do that yet.
I might take something really simple like this constant. Then what's the Q?
Operator of multiplication by constant.
Does it have
I mean H. Identity operator, I think, yes, Q will use just identity. So I will actually right now, yeah, I think,
the identity.
yes, so I can actually not, yeah, I think so. Okay, so there is some operator theoretical interpretation of this Q, which might answer your question better.
Okay.
So, I already told you this, by the way, but probably. Yes, so let's look at this limit 1 over Cx of t. So it's unbounded operator, so there are some problems with strong convergence, so we need to be in the domain. So let's try to kind of renormalize it as a question for bounded operators. So to do it, let's say that, okay, so 1 over t x of t equals 1 over t x of 0 plus integral from 0 to t x prime of t dt. Just Newton-Leibniz formula. And then we can actually forget about this term, because if we are in the domain of x, then this will just converge to 0. So this all is about this limit. And x prime of t is actually something very simple. So, okay, so I'll write approximate, because it's equality only in the limit. So I want to forget about this term. 1 over t, integral from 0 to t. Okay, so e to the I ht, the commutator h and x, negative I ht. And there's also I guess, here. So if we differentiate x with respect to t, then you get h from left and h from right, which can be put inside, then you get the commutator. And the commutator of h and x is a nice bounded operator, which basically looks like this. So let's denote this operator. Okay, so A equals I hx, which is actually equal to I. So there are zeros on the diagonal, 1 above the diagonal, negative 1 below the diagonal. So it's kind of a discrete version of the gradient operator. And we are interested in this long time Cesaro average of this discrete gradient operator. So this is the,
What did you call it? Discrete gradient?
well, I would call it discrete gradient, because in the continuous case,
That's what it would be.
in this continuous case, it would be just the usual gradient.
Because you commutator velocity with x.
Yes. So it's some statement about convergence of a sequence of bounded operators.
It's your momentum, right?
Yes, it's a momentum operator, and this is kind of the asymptotic momentum or asymptotic velocity.
And so that's just the commutator of the Laplacian with x, right?
Yes, because x commutes with the potential, and so you only get commutator with Laplacian, which ends up this. Okay, so this is first operator theoretical reformulation on bounded operators, but actually there is some nicer interpretation, which was also used in these papers. So basically, okay, so let me say what we want to do. So we want to compute this operator for some classes of Schrodinger operators with AC spectrum. For example, for periodic and quasi-periodic. And it turns out that if H has point spectrum, so if H has purely point spectrum, then this operator has actually a very nice interpretation. So suppose that sigma of H is purely point. This is not the case we're interested in because we're interested in something opposite, but it's a case where this operator can be computed very easily. So then H is the sum lambda j psi j, just spectral decomposition. And a simple computation shows that this Q will actually be the sum A psi j psi j psi j psi j. So I'm committing a sin here by mixing two different notations, the dot product notation and bracket notation, but I think it's okay. So what exactly is this? Basically, if we look at the operator A in the representation of eigenfunctions of H, this is just the diagonal part of A. So basically, this procedure just takes the diagonal truncation of operator A with respect to the eigenbasis of H. And this seems like maybe this is a complete operator-theoretical answer, but unfortunately, I don't know of any notion of diagonal truncation for continuous spectrum. In fact, there are some papers which said that notion with good properties does not exist. I mean, maybe for smaller class of operators it does exist, but in general, I don't think there is a good definition. Yes, and the proof of this is actually quite easy. So you just plug this formula into that formula and see that if for terms which contain two different eigenvalues, you will have oscillations which will ultimately kill them. So you only get what's on the diagonal. You'll get something like sine of lambda I minus lambda jt divided by t.
You don't have to have any non-resonance condition to make sure that's okay.
For strong convergence, we don't. I mean, if there are eigenvalues of multiplicity more than one, then we get projection here, and then even if we don't, it's not a problem. So here, then, okay. So more correct version would be that instead we take the projections of whatever dimension they are, and here we'll get something pj, a pj.
Yeah.
So it's not really a problem for strong convergence here. Okay, but now.
So you don't need to know how fast it goes to it or something like that.
We don't in this formulation. We don't. We just need eventual strong convergence.
But I guess if you're going to ask how quickly it goes, then you might.
Oh yes, how quickly it goes, it's a completely different question. Yeah.
Worry about small divisors.
Yeah. Yes, that would be a problem about small divisors. And yes, so the reason why it works so well is that the convergence is strong, not operator norm.
Yeah.
For operator norm, it won't work. And for weak convergence, it's not enough for us. I think weak convergence is actually something that's easier to show, but it might. I mean, okay, so there is actually always some subsequence that converges weakly because the ball in the set bounded ball in operators is weakly compact. But then we have problems with uniqueness of limit and everything.
Yeah.
So we need strong convergence here, at least for the approach that we use. Okay, but this example is artificial. We are not really interested in operator with point spectrum. So what to do when we have AC spectrum? And turns out that in the periodic case, we can reduce it to the case with point spectrum. And the reduction is actually quite simple. So first, periodic case. So I'm basically telling you what Domanic, Lukic, and Jessen did, and also Esch and Knauf. So periodic case. So any periodic operator can be decomposed into Floquet waves. So is everyone familiar with Floquet decomposition, or you want? Okay, I guess I'll assume that. So so any operator with periodic coefficients is actually a direct integral of some operators on the period. So 0, 1, h of k, dk. So where h of k, so in a discrete case, are just finite matrices on the period. So h of k is basically just, so we restrict the potential to the period, -1, this is Laplacian, zeros, e to the 2 pi ik, e to the negative 2 pi ik. There is a simple explanation of this. Basically, operator commutes with translations, so we can look at eigenfunctions, which are also eigenfunctions with translation, and we get exactly this. Sorry, I'm just to make sure that. Okay, and now what we can do? So when we try to compute this limit for h, we can we can just compute it on each fiber separately. On each fiber, it will be just an operator with point spectrum because it's a matrix. And then you get the answer. Then you direct integrate the answer to get the answer for the original operator. So the less trivial thing is to show that the kernel is 0, and that follows from the structure of this operator. So this is what the Manic location Nielsen did. There is another result by Jake Filmans, who extended this to limit periodic operators.
And you can, I guess in special cases, you can probably compute this Q, right?
Yes, so this Q will involve derivatives of the eigenvalues of this as functions of quasi-momenta.
I see.
So it's kind of the average group velocity, sort of.
Ah, yeah.
Yeah, if I have time, I'll mention something like that holds in quasi-periodic case as well. Maybe I'll have time to mention that. Okay, so for periodic operators, it's simple. For limit periodic operators, you can, if operator is sufficiently well approximable by periodic ones, it can also be done. Same method. It was done by Jake Filman. Now, what about quasi-periodic case? So let me now move to the main results.
So
yeah.
just to back up a minute. So once you have this result about the limit,
Yes.
then that's sufficient for you to control the time evolution, or to get a bound on the velocity.
Yes. So once we have the limit, actually this v0 will be greater or equal than norm of q.
Greater than what?
Than the norm of the operator q. Okay. So like maximal eigenvalue, sort of, which if it exists. Okay. So now quasi-periodic operators. So basically, first, why quasi-periodic operators? Why we're interested? It's just because there are, in general, there are not so many classes of operators to this spectrum. So you can say quasi-periodic, some limit periodic, maybe compact perturbations of the Laplacian, which is something probably not difficult to cover by scattering theory, and that's it. Well,
That's about it, right?
yeah, I mean there are some also reflectionless classes, but yeah, that's maybe next general. Yes, so it was a natural question to see if the same thing holds for quasi-periodic case. So what's a quasi-periodic operator? So let's say we have a function on the circle, analytic, and then quasi-periodic operator family. Okay, let me first write down the definition. Alpha is irrational. Okay, so if alpha was rational, then this would be a periodic operator. Now we have potential generated from the trajectory of rotation. And it's natural to consider not just a single operator, but a family of operators. So it's a standard thing. Ergodic family of operators, they have a lot of properties in common. For example, they have the same spectrum as a set. They have almost surely the same type of the spectrum and a lot of things. And in general, sometimes it's easier to prove a statement that holds for almost every x than to prove it for every single operator. Okay, so what's known about the spectra of these operators? So what kind of regimes we are going to be working in? So there are several situations where AC spectrum is established. Okay, so let me formulate it like this. So if lambda less or equal than some lambda 0, which depends on lambda v, we have sigma AC. So here there is no condition on the frequency. So this is the recent results follow from Avila-Fayat-Krikorian. Okay, so this for Diophantine frequencies is Bourgain and Zhytomyrskaya. For non-Diophantine, it follows from results of Avila, Fayat, and Krikorian.
So your results you don't care what x is, and you don't care what alpha is.
So in my results, I still need alpha Diophantine because I will need something better than just sigma AC. So the results of Zhang and Zhao, which I mentioned, actually work for all alpha, but they are not as strong. Yeah. Okay, and if lambda is very large, then there is purely point spectrum for almost every alpha.
So this is true for all V?
For all analytic V, yes. analytic quasi-periodic. So reference is Bourgain-Zhytomyrsky, Ilya-Kachkovskiy, and this is Bourgain-Goldstein. I can give you more precise references if you want. Yes, but these are all now non-perturbative results, which is kind of good. So there is no dependence on alpha, which was a big thing actually, because perturbative results were like 20 years before that. I think Tom has also some.
Yeah, no, I mean,
think about
you're
that.
doing it for almost, yeah, that's a little different from what we did. We fixed alpha and then we did it for almost
Yes,
all x.
yes. This is still for almost all x also. This is for almost all both. So, okay,
You
yeah.
take out a set of measure 0 already from the irrationals.
Doesn't matter. I mean, for this doesn't matter because if it's rational, the spectra is also AC.
Okay.
It's
But-
because
but
periodic.
Does almost every alpha just mean alpha rational? Or
No, it actually means a much smaller set. So if we of course need to take out rationals, we need to this alpha needs to be Diophantine, otherwise it won't work. But so for almost matchy operator, Diophantine is enough. For general V, there is some additional exclusion of frequencies, which is not really arithmetic, but it's known to be measure 0. It comes from this semi-algebraic approach. Okay, so and basically the result that we have works in this regime, but for Diophantine frequencies. So let me explain quickly what's going on. So I need to introduce the concepts of Aubry duality. So for almost Mathieu operator, so almost Mathieu, there are two regimes. So almost Mathieu means V of x equals 2 cosine x. Then the transition point is actually lambda equals 1. AC, lambda greater than 1, purely point, almost every alpha. So an almost Mathieu operator has some additional symmetry because we can do Fourier transform, then cosine will interchange with the Laplacian. So we need to do something more clever than Fourier transform because we also need to take care of this x plus n alpha. So this transformation is called Aubry duality. And basically, the precise formulation would be the following, that if we not just look at, okay, so the dual operator looks like this. So h hat psi m equals v hat psi lambda convolution psi m plus 2 cosine m alpha plus theta psi m. This is so-called dual operator. So it depends on the ergodic parameter theta. And basically the usual intuition is that it interchanges small coupling and large coupling.
This is basically Fourier transform, right?
Yes, basically it's Fourier transform. So, but it's not a unitary equivalence on the level of x and theta because they have different types of spectra. It's a unitary equivalence on the level of direct integrals. So integral h of x dx is unitary equivalent to that direct integral of h hat of theta d theta. So the operator and the fibers have different spectra, but this difference comes from slicing the same integral into fibers in different ways.
No, I never thought about that, but
Yes, yeah, this is something which is known. And basically the intuition is the following, that if we have point spectrum here, so in many cases there should be AC spectrum here. For example, this result Bourgain and Zhytomyrsky was proved this way. So they proved localization for the dual model, and then by duality they proved AC spectrum. So Avila-Fayette-Krikorian is AC spectrum independently of localization. So it starts with they prove something that's called reducibility, which is kind of dynamical description of AC spectrum. And then there was a result by
it's conjugated, so it looks like a
yes. So there are nice eigenfunctions which behave like Bloch waves. Sorry, I'm not being very precise here, but I want to explain just the idea basically. And then the result that we have is the following. So suppose that we are in the regime where we have reducibility, then there is actually a proof that the dual model has a point spectrum. So we have a result in the other direction. It's a joint result with me and Lana. And then what can we do? So we need to compute the operator Q, which I mentioned before. So instead of computing it for single h of x, let's try to compute it for this family. And then, yes, then by duality, we can make some transformations and compute it for this family. For this family, we now have fibers with point spectrum just as in the periodic case. So we can use that point spectrum argument on the fibers, then find the limit, then transform it back. So we lose some information during this transformation. So we only get it for almost every x, this strong ballistic transport. And also, we only have the existence of strong limit on some sequence of time scales. So this comes from technical statement about integrals. Basically, if you have convergence of something L2, then there is a subsequence that converges almost everywhere. So this would be that subsequence. So we have strong ballistic transport for a class of quasi-periodic operators with AC spectrum on its subsequence of time scales, but it's still enough to show that Lieb-Robinson velocity is bounded from below. Okay, but basically just some conclusion maybe that what I think is really interesting is, okay, I think I erased everything. So is there any abstract version of this operator Q?
No, just
Oh yeah, it's here. Oh, yeah.
The Operator-theoretic doesn't use the fact that you're doing almost mature, right? You can do that for anything.
Yes, Operator-theoretic works for any V. So originally we have this operator. The dual one will be a non-local operator with non-local kinetic energy part, but the potential will be very simple.
So you don't have to use cosine structure. You can have a sum of cosines. You're fine.
Okay, so it's not so. Okay, so we need Laplace at least in one of the regimes, because we work with the dynamics and we need transfer matrices. So there are some possibility to do it. So if instead of Laplacian we have some non-local operator but of finite range, then it's going to be co-cycles of larger dimension. It's currently a question we might be considering with Chris Marks maybe, if he's interested. Yes, but what I was going to say. So all the examples in which this operator Q has been computed, one way or another, reduce to some situation where we can find point spectrum.
Yeah.
But it's not really, it has nothing to do with point spectrum. It's a property of system with AC spectrum. So I think there should be some like abstract version of criteria of existence of this limit for operators with AC spectrum. So probably maybe the same as the difference between Kohtani theory and Remling theory. So Kohtani theory said that like ergodic operator families with AC spectrum are reflectionless, and then Remling proved a deterministic version of that. He basically said which exactly operators with AC spectrum are reflectionless, sort of. So it would be nice to do something like that, but I currently don't really have any good.
You'd like to be able to say that has a limit and without maybe using as much structure as you do?
Yes, exactly. So I want to find out which structure of AC spectrum is responsible for the limit. So I think it also has something to do with reflectionless, but I don't have any good conjecture. So basically, it's a statement that wave packet stabilizes on infinity if you normalize it, but
It's a kind of homogenization, as we were discussing. I think it's a kind of homogenization.
Possibly, yes. Maybe we need to look into that.
Some ergodic theory, perhaps. I don't know. Well, no, you don't need it because you don't have that problem with the periodic, and it's not ergodic. I mean, I can shift things around.
Well, periodic is not ergodic, but it has even better structure in a sense.
Yeah.
So if you it's decomposable into some even more simple. Here we also have some kind of decomposition. So if it's not visible on the level of h of x, but it's visible on the level of direct integrals.
So you're really using this Operator-duality quite
yes.
quickly.
So okay, so let me formulate it like this. So everything is known about this Q is proved for systems which are decomposable into point spectrum.
Yeah.
Even for this case, ultimately it's proved for the system.
Of course, you can't just use AC spectrum because presumably it's false in the case of a random, a random one where I have presumably have diffusion.
Well, random. It's one-dimensional thing.
Yeah, well, you don't.
So one-dimensional random.
Yeah, no, I don't mean one-dimensional random. That would be localized, but are you? Yeah, of course you're using the one-dimensional structure very heavily here.
Yes, I'm heavily using one-dimensional structure here. Otherwise, I mean, it's not always in higher dimensions. It's not always natural to expect ballistic transport. Usually, it's like t to the power 1 over d. At least this is the Jarneri-Combs version for multi-dimensions. Okay, so basically that's all I wanted to say. Just I think this abstract version of Q would be really interesting, but I don't really know anything how to do it.